My talk was about building a GPT from scratch. Over Christmas holidays, I basically did that. And Vasu mentioned Karpathy. He's a famous person in this area because he made lots of YouTube videos and he started a NanoChat project. And in some of his videos, he said, don't just read the code, watch the videos, just do it on your own. And I always wanted to do it. And over Christmas, I just did that. And you will see and maybe learn something from this journey. And so in German meetup. So what we did here, started with some friends, originally NanoChat, right? Schnacken, Northern German, is something like chat, so NanoChat. And this is it's a model, it's a GPT-2 model, like Andrej Karpathy also does, but everything is from scratch. Like I haven't looked on the code of NanoChat. It's completely independent because I wanted to learn, right? And if you look here into the model folder, you will just find lots of Python files. And there's one which is called GPT, and there's a core of it. And I bet you will more or less understand after the talk what is in there. But you will not see much Python today. So if this toy here, maybe you know it from your children, like vectors. Everything is about vectors today. So lots about linear algebra. You might remember first year of university or Fachhochschule or something like that. Maybe 11th grade at school. That's the topic today. And it's enough. This is like the interesting thing, right? This book here, like the first semester, is enough to understand LLMs. Okay, so we take this NanoChat and we deploy it. We want to train today a model. So I went to this vast AI website. It's a broker for GPUs. So you can get a cluster, a Q cluster, but you can also get just a Docker container where you have access to GPUs. And I have to see, so we have a Bulgarian 2100 machine here. So this costs like $3 per hour. And I just booked that. It takes a moment until it's active. And the H100 is like the middle class GPU from NVIDIA. And it's a device like a normal graphics card from gaming, costs like $30,000 originally, I think, in this dimension. And you get it for an hour for $3, right? Okay, so while this is warming up here, so this takes a time, let's go to the slides again. So why did I put this eBay page here? So I'm tempted to buy this thing because I think it's awesome. And I will tell you why. It's a console from 82. And the interesting thing is, so first of all, if you haven't visited the Offenbach Retro Computer Park, there's a museum by some nerds. All the home computers go there. They have this device as well. The cool thing about this is they are vectors. Like the game graphics is not scan lines like you know from a TV and the home computers in the 80s. The computer program, like the game logic, moves the ray of the cathode ray tube. And of course, this is very different to what we know from the years after, right? But this existed in the 80s. So it's a very interesting device just for historical reasons. Who knows that? What's the name? F-14. That's a Tomcat jet, right? What is special about that? Yeah, there's Tornado. It's better. But what is special about that? Computer science, IT. It was the first jet which had a microprocessor for flight control. And there's lots of information. There's a very long and interesting YouTube. There's a website about that. And the interesting thing is this was in the 70s, 1970. So there was development, everything, of course, super closed and nobody knew about that other than the military people. And there was a 20-bit microprocessor built for this plane. And at the same time, Intel worked in parallel in the open and they built a 4-bit machine or 4-bit processor. And this was not known, right, to Intel. Maybe they had some connections, nobody knows really, but it was the first machine, the first airplane which had such a processor. 20 bits because it was specialized for the flight dynamics, obviously, and you need some precision there, so that's why they need the bits. It was a microprocessor, but of course not that generic like an Intel processor maybe, but it was a real microprocessor. All right, so a bit more about history. Here with Chris, we went to the Computer Museum in Palo Alto. Computer History Museum. And there was a section, Chris might remember, about computers before digital CPUs, analog computers. And when you think about like those rockets here, those intermediate range rockets they built into, or they were installed in the UK, of course, in the Cold War, 56. Those had analog computers here in the control unit on the device, on the rocket. So they didn't have digital computers at the time. They had them, but not in the size probably and reliability they needed. So it was analog. On the ground, they had digital computers. And actually, you hear when you see the terms metrics, cost product, this is all something we will see in the LLM in a few slides. So why digital computers? Because they had to solve differential equations to compute how the rocket has to fly through the orbit. And this was just too hard for doing it on the rocket itself. If you go 20 years before that, in the 30s, they wanted to build those rockets at the time. And what they did, they didn't have computers, not even like, I mean, you know the history about computers. There were some which looked like computers, but to solve differential equations, and somebody will notice this is a clean Baukasten from the time, they built mechanical differential integration devices. So they could solve basically physical problems by mechanics, right? And this worked, and they used that. And yeah, there are several pictures here. And out of this development, of course, then the rockets came and eventually the planes and so on. All right, why do I talk about that? I talk about that because analog computers are very similar to LLMs. LLMs are analog computers. That's my pitch, my claim. You will understand in a second why. Okay, so let's see how our purchase went here. So we have a machine, it's up, so I copy SSH, I go into my console, log in, yeah, of course, accept everything here, so there we go. Tmux, and I put a script in our repository, bootstrap sh. It just checks out the repository and installs UV. UV is a Python package manager. And I just run that here. And again, we have to switch back to the slides because this takes a moment. It just downloads Python packages and everything before we can actually start training. All right, so analog computers, analog LLMs. So what do LLMs do? And you might have read that here and there. They do next word prediction, right? There's one task. You take a sentence from the internet, something like my example sentence here is the cat sits on what table, right? And you can ask the pre-trained LLM, like, yeah, they are available. Like you can download GPT-2, for example. It will tell you like cats often sit on tables, like it's the most probable subject or word here. They might sit on floors, on mats, on roofs, on chairs, but table is the most common one. And this is the main task, or it's the only task you train on. Very simple, just guess the next word of a sentence, right? Actually, I'm not really precise. What they really compute is they take the sentence and they tell you the next word after is something. So the next word after cat is something. So it computes more than we actually want. But in a chat, when you are in ChatGPT, everything here is thrown away because you just want to have the next word. All right, so you could do that. Not really, because if you do that here, those companies, they train models like base models, pre-trained models, and then they make them into chatbots. And chatbots are more, they follow a dialogue. It's not the completion of the word. So they have a post-training, which makes them into a chat dialogue machine, basically. So it's a bit different, but what they're building before publishing the product is the next word prediction model, the pre-trained model. And yeah, if you look on that, how you use such a model, and some of you will have used like some services or local models before, there's the word or the term context. So you basically it's the input. So you take a sentence like the cat sits on the, you feed it into the model runs one forward pass, that's what you call that. It will tell you table, right? And then you take the table, append it to your input, and then you do a second run. ask the model, now the cat sits on the table, what is the next one? Yeah, maybe if it's well trained, it's in. And you do that word by word, and eventually it will tell you end of sentence. So then you have the cat sits on the table in the living room, right? And because you feed the output again into the input, yeah, there's one term you will see, it's auto-regressive. So it's like recursive kind of thing. Auto-regressive models. All right, so bit about history again, papers. So there was in 2017, there was a famous attention is all you need paper from some Google people. And they built a model for translation. Here it has two parts in the architecture. On the left, you put in like a German sentence, and on the right, the model computes the English sentence. And 2 years later, OpenAI published a GPT-2 paper here on the left, 2019. And 1 year later, 2020, the GPT-3 model paper. And the model here, which says the architecture looks very similar to the previous one, but it's simplified. It just has one pass, like it's just the right side, basically. All right, so let's see how our machine is. So everything is installed. That's cool. And so I bought a machine, I think with 4 GPUs. Did anybody remember? I think so. But we are starting just with using one of them. And just make train. So it calls Python now, starts the training. Everything is based on PyTorch. PyTorch is a library to do training, to define models and do training. And so you see lots of values here. And I promise you, 1 second, where is it? Scroll up, it's Tmax. I'm not the Tmax user. But here's the architecture. And after the talk, you will understand, I think, yeah, all the values here. Just one, I think, is not really mentioned, but everything else we understand. All right, so again, this will take time. How do I get out here? Escape? No, okay. All right, it's downloading now data from Hugging Face. Hugging Face is a website where you can upload and download datasets. And on Hugging Face, so I show that here, if you go back to my browser, the yellow icon, so here's my NanoChat collection. Like they are basically copies of the German internet, like datasets, gigabytes of data, German websites. And there is YouTube transcripts of all German videos, for example. There's the Wikipedia copy, here's the last one. Everything German in Wikipedia. And you're using that for training. So takes those data sets and feeds them into the model. But it takes time, so there's lots of priming of the cache. Like the machine was empty, there's no cache, right? So it downloads stuff now. And yeah, now it's waiting for the actual first data, but let it just go through that and we can take a look later on again. All right, my motivation, and I guess many will have the same feeling. Everybody knows that, right? What is it for Neumann machine? That's you learn in school or in university. It's this architecture of memory and CPU, and there might be secondary storage. There's an ALU which does the computation, and there are caches. And everybody can imagine, like every engineer knows by looking at that, if you build a machine big enough, you can boot a Linux kernel, right? This is somehow intuition. And here's John von Neumann in 52 in front of his machine. Probably it's an electric mechanical machine, but basically scaling this one up could run Linux, right? In theory. But for LLMs, you don't, right? This connection, this intuition is completely gone. Why does this work? It's a magic black box. And if you want to understand LLMs, you must understand 2 things. Like we have this architecture, I will explain all the components, but there are 2 tasks to do. One is, can this architecture compute interesting algorithms or logical structure in sentences? Can it, like the architecture, is it able, if I put all the parameters, like there are many parameters in the matrices, right? And they are all learned by training, but can it do interesting things just by the architecture? That's the first question. Second question is, can we train, like can we, when we inject enough data into this model and train like hours, days, months, does it converge to those interesting functions it implements? Like, does it implement the best thing possible, basically? And there's a third requirement, this is special for training. You need data, right? If you don't have data for next word prediction, you cannot train. But luckily we have the internet, there's lots of text of the last decade and more. So we have data to train next word prediction. So, oh, this is perfect, perfect timing. So it's learning now, and you see steps here. You are seeing that it does like 270K, like 270 words per second training. And you already see something here. This is the most interesting function every AI training scientist will look at all the time in the night on the mobile. And when this doesn't go down, this person will get nervous. This is the goal. This is the loss function. How good is our model, right? Our model here, it has a certain size, and the logical, like the theoretical maximum of this loss function is like 12, I think. But we want to go down to 2, 3, right? And yeah, you also see my test sentence is not very interesting yet. So it's still very dumb, doesn't speak German basically. So die Hauptstadt von Deutschland ist. Already there's an ist, this is incredible. Could be something completely stupid. But it got that, right? And this will get better over the talk. And then, yeah, you see the material we're training on. So YouTube is on that. Wikipedia is on that. This, I think, is 1 million whatever posts from the internet. Lots of data from German internet. Okay, so Q, somebody said, right? Yeah, this works. And we just let it go, let it work. And tokens, what's a token? Everybody knows tokens, right? But what is it? And to understand that, we need a tokenizer. And who knows the sentence or this text here? This is Goethe's Faust, I think, right? Some sentence out of that. And it doesn't matter, it's just an example. And what we want to implement to build a tokenizer is byte pair encoding. And it's an algorithm as simple as the name suggests. It builds byte pairs and names them. It's from 2016, but there's history. But basically what it does, we are counting byte pairs. So we are taking a look here, which are common, like CH, if I remember, is the most common one. Like CH, you will find 9 times if you count correctly here in the sentence. And of course, I don't want to do that manually, so I asked Claude to do that, and it was counting. So CH is 9 times, EN is 8 times, and so on. And what this algorithm is doing, it's replacing the CH, like the most common 2-character combination, by the next token number. We have ASCII text, so the ASCII has 256, so 0 to 255. Next one is 256, and we replace that, right? And we continue. We do the same thing again. So now every CH is the 256 here, and we take the next one. So now EN is the most common one. So we replace EN, but it's recursive. So it could be that like a new token, in this case here, 256 space, is even, it happens four times, right? And you can imagine you continue that. And the question is how long? We continued that like 32,000 times. So quite a bit. Here, the next one, ER. And if you do that, you come to a tokenizer. So NanoChat is our token. So we call it NanoChat 2. It's our tokenizer. And every color here in the word is now a token. And you see the numbers here below. And some words are 1 token, which is good. Like Anfang, Wort, das, they are all 1 token combinations, even low numbers, which is also good. But some like geschrieben needs 2, and it needs 1, which is pretty big here. Maybe because geschrieben starts with a big letter here, capital letter, which doesn't happen so often for geschrieben, obviously. But basically, this is what happens. And yeah, we had a bug in the tokenizer, we realized. Like every time here is an umlaut, this somehow breaks. So this doesn't cope well with umlauts. It's not that bad. Like the model can learn around that, but it's not good. It removes capacity of the model. GPT-2 uses a higher, bigger count here. So they use 56,000 for reasons, whatever. And but it's trained on English data. So, and you see already, so the same text needs 109 tokens, not 84, because ours is German. This was specialized for English. When we did that, we thought GPT-2, they will have German inside their data set, right? No, they didn't at the time. So that's why we took a smaller number. Maybe nowadays we would take a bigger one. And there's this nice TikTokenizer, nice word game, right? Just Google for it. You can try all the tokenizers which I use, GPT-4 and so on. They're even bigger. They have more words. Okay, so we have something like a tokenization of a sentence. And yeah, as I said, it's good when there are less tokens, because tokens take space and compute power of a model. That's why you should talk English to your GPT, not German, because it's better for English. At least needs less tokens, is much more capable if we do. So next thing is, so we have 32,000 something tokens, and you need 50 bits for that, right? 2 to the power 15. So I talked about analog computers before. Analog computers, what does it mean? It needs analog numbers, right? Real numbers, not digital numbers. What one does here, one doesn't use the tokens directly, but one uses vectors of real numbers. Like there are, in my model here, in our model, NanoChat, there are 768 dimensions in those vectors, like 768 real numbers. And just to have an idea here, if we want to put our 15 bits in here, there's lots of space which is unused. Okay, so those dimensions are many, many more than we need. And even you can compress that, right? Binary 0, 1. Real numbers have so many variations, right? You could compress it to 0, 1, -1 and save space. So, and you can improve that, right? You can even compress more. Lots of space in those vectors. But those vectors we'll see all the time again, and they're called embeddings of the tokens. Every token, every word, basically, every cat sits, every of those tokens gets a unique vector. And the model will train that, will learn that. What the vectors are. They are not like that. This is just an example, right? It will just start random and then optimize. And eventually there will be one vector, one embedding vector of this length per token. All right, so going back here, I'm not sure it's already worthwhile. Oh yeah, maybe, look here. Getting better. Die Hauptstadt von Deutschland, it's becoming German, right? And it's becoming German after how many? 1 million tokens. So we piped in 1 million words basically from the internet. And it's already speaking something like, sounds like German. It's not really, it doesn't make much sense, but we're getting there. All right, tokens. So I took some not famous, but prominent ones like Berlin, Dresden, Wiesbaden. They are all one token words. And I figured, like I tried that some days ago, and I was very disappointed that Berlin needs like 3 tokens. Until I realized the tokenizer learns the space in front as well. So this is 1 token for the tokenizer. So I had to put a space in front, and then all those words are 1 token. And then, yeah, what is not 1 token? Everything about umlaut, obviously. There's a bug, I guess, can be improved. Here, Donau-Dampfschifffahrtsgesellschaftskapitän, something. It's long. I looked for food in Heidelberg, and you can tell me whether it's correct or not. Claude told me Bratwurst, Saumagen, and Dampfnudel. They are also not 1. And by the number you see, like when in this byte pair algorithm, this token was generated, right? So it says something like a high number means it was in the 32,000, but very late. Right? But words like, I don't know, Mann, Frau, Hund, they are much earlier in the 4-digit ones here. And what the model also learns, and this is already the first point where you could be amazed what happens here. You can compare vectors. You can compare the embeddings. And we will come to that, how this works. And when you do that, Berlin, Hauptstadt, they are similar. It's a positive number, not really big. Deutschland, Frankreich is bigger, right? It's more similar in a sense. And you can do Vater, Mutter, Hund, Katze, and so on. Bier Sachsen, for some reason, this is kind of common. Lehrer don't drink so much beer, I don't know, and Vater and Wiesbaden is even negative. So, but there's already some meaning in those embeddings, right? That's the impression you get from that. All right, so I promised linear algebra, right? First semester is my vector toy, and we will use that at some point. Before doing that, before looking into more interesting bits, just some notation. This is always our embedding. Like here is a 768, like the dimension of the embeddings. Like this could be cat, right? Or could be table, one of this vector. And then we have a matrix here, and it has 3 lines, 3 rows. And in my head, when I multiply matrices, I take this vector, I turn it around, put it here, and then I compute the scalar product. And you might remember from your school time or university doing that. And the result is like 3 lines means the result are also 3 values, but values like real numbers. So we have basically turned a big embedding into a smaller vector space. So from 768 to 64. And you can do that, like you know that here's 3 dimensions, right? Red, green, and blue. And the yellow here, this one in the middle, that's 3D. So it's a vector in 3D. And you can project it into the plane here, right? So you can reduce from 3-dimensional to 2-dimensional, right? And you might have calculated that at school or university. And there's one more interesting thing. So we just looked on embeddings and similarity, like Mann, Frau, and so on. And how you do that, you take the dot product, in German scalar product, right? You remember that. It's also it's a matrix multiplication, but with vectors. Here's one row, 1 column, and 1 row. And if you do the same thing, you get 1 number. And the intuition is here in the 3D or even in higher dimensions, when they're orthogonal, you get a 0. When they are kind of pointing into the same direction, you get a positive number. And if like the angle is more similar, like I put here, the number gets bigger. And if they go into opposite direction, they become negative, right? But it's something like similarity, and this is important. And we saw it here in the picture here, the comparison already. Okay, so now I promise you the most complex part of the talk. Everything else will be intuition. This is a bit of mathematics, not much. Everything is 11th grade, so not too much. But you can imagine, so we have a model like the one that here in the papers, this was proposed, right? And our model has 111 million values. Like there are matrices inside and 100 million values, real numbers. And what we do here in the training, what this thing does, it's all it does. It takes the current state of our model. We start actually with random numbers. We start with random numbers here, and we take one sentence of the internet, the cat sits, right? And we compute the next word for every of those words. Next word of sits, we would like to have on, right? The cat sits on. On is the next one. That's our hope. The next word of cat should be sits. The next word of the should be cat, right? But the model is not good, so it tells us instead of cat sits on, it tells us car eats, right? Not good, but already quite good because car and cat, they are like not verbs. Eats and sits are verbs, and right and on are prepositions, so there's always similarity. And then you compute the loss. We have seen the loss here, like the curve which went down, right? And the loss is also here in the lines somewhere. Where is it? I don't see it in front of me.
Right in the middle.
Right in the middle. Oh, yeah, here. So we had 4, roughly 4. This is the loss. And the loss is done by subtracting the embeddings, the vectors, the red vectors, and then taking basically the square of the length. So we take the difference, how far are we from what we want, and then we compute the length of this delta. And this is our loss. It's a number, right? And our goal is to make this smaller and smaller. When the model is really good, the red here will be more or less equal to the green. And then it's more or less 0. It's not 0, it's like 2 you can reach, I think, but 2.5 or something. Okay, this is our goal, but how to do that? And again, this is now 11th grade. You might remember this notation when you did Ableitung in German, deriving derivatives of functions. Usually it was like you derive f to x, right? This dx thing everybody knows and remembers. And this is basically that we want to derive how does the loss change if I modify one element here in the matrix, this element, right? So it's like a derivation of the f function to x. And when the derivative is positive, then increasing the value here has a bad impact. You will see in a second why. So if it has a bad impact, then inverse direction, make it smaller, right? If the derivative is 0, doesn't matter, leave it where it is. If it's negative, make it bigger. And this looks abstract, but let's do it concrete. Everybody knows quadratic function. And the red one is where we are. This is our the car eats right, or what I had there as example. And this is a cat sits on. And we want to go to the green, right? And if the derivative, like the slope here of this function, of the quadratic function, if it's negative, we have to go to the right. And if we were here and it's positive, go to the left, right? That's what it is. And some of you will have done this in higher dimensions at university. You can do the same derivations in vectors and in matrices. Jacobi matrix, gradients, these kinds. The topic. And, from mathematics of the 11th grade. Chain rule in German, Kettenregel. That's the only one which you really need. And there's one more thing you need, and we just took it for granted. You cannot take a derivative of everything. I mean, here's a max function, the max function which cannot be derived here at 0, right? There's no value. But luckily, you can define it. You can say, okay, just take 0. Doesn't matter. It's just 1 point. We don't care what's the point, right? Everything else of the function is good. Matrices can be derived. This is easy. There's something like a layer norm. We'll see. This is just a sum plus can be derived. It's easy. Quadratic functions can be derived. Square roots, quotients can be derived. There's a softmax which shows up in LLMs a lot, which is also just an e function, exponential function divided by a sum. Everything in the model is of this kind. And this is by design. Like we do that because you will see in a second why. We do that because we want to learn, right? And I didn't mention the terms here. Gradient descent. Gradient is basically the best way to go down in a function. You'll see it in the picture in a second. Backpropagation is also a term. It's the same thing, more or less. Backpropagation is basically what you saw on the first slide. And then there's deep learning. Sounds great, right? This is just this topic, nothing else. All right, and the training loop, which runs here, PyTorch, right, looks like that. And you have seen those steps already. So you compute, you take a sentence of the internet, move it through the model, you get hopefully a good completion. You compute how far are you from the completion in the internet compared to the one you actually got, compute the loss. And then PyTorch is so elegant, or it's so powerful, it can do the derivations for you. But you could do that manually, just on manually on paper. And the first step is the forward pass, because it moves forward to the model. And because you have to derive something by going backwards, it's called the backwards pass. And yeah, this is all which is done with the big loop in front. Do that for 10 billion tokens. There's a rule of thumb, at least 20 times the model size should be the input. Then the model is doing something sensible. So we need something like 3 billion tokens or so. Now we are at 10% of that. All right, so I do something and I'm not sure this works. We will see. So I press Control C and you might be frightened. Did we lose the data? No, we didn't. There are checkpoints regularly. So it's stored on disk like 1 dot something gigabyte. It's a whole model. And what we do now, we paid for 4 GPUs, right? And we only used 1. Not a good deal. So let's fix that. And there is torch run here, and I can never remember the parameters. That's why I copy them. We have 2? Are you sure? Oh, we can check. You can check. Oh, they're just 2. Okay, it would have told us, I think. Pretty sure. This wouldn't work. Anyway, so we take our command. The batch size I take leaves the same. So batch size is set there because our model is small, and we have 80 gigabytes of memory in each GPU. So that's why we compute 80 of those completions in parallel. Not 80, 64, I think. And the goal, of course, is to use as much of the GPU power as you can, right? Obviously. So let's do that, but not 8. We only have 2. And everybody who has done Python, Python doesn't have coroutines like Golang or other languages or threads or something. Torch run just starts 2 processes now. And it gives them an environment variable called rank. And the one with rank 0 is printing. The other one is just quiet, but does the same work. And they synchronize once in a while, like every batch, I think. They compute the 64. Yeah, I didn't say it before. So one sentence is 1024 tokens in my case, and I do 64 in parallel of them. And after that, they synchronize, they take all their corrections of the matrix. We saw that, right? How you correct the elements in the matrix. It does that every 64 batches, and then all of them have the same state again. But it's really, really very naive, like feels like 1997 or so from the technology. Feels awkward if you have used another language before. So this takes long again to start up because it has to call Hugging Face, and I'm not a paying customer and so on. So it takes time. All right. Gradient is basically the direction the ball should roll here, right? If you put a ball here, it will go down. And our goal is to reach the minimum, the absolute minimum, right? Here's danger, right? We could end up here or even here, then we have bad luck. Why doesn't this happen? Any idea? So bad luck in 2D means we are on a local minimum here, right? First derivation is 0. That's the definition of such a minimum. But then you might remember from school, second derivative can be positive or negative. If it's positive, it's a local minimum like here. If it's negative, it's something like, you remember that, like a function which goes like that, right? So I think subtle was the word, maybe, I remember. So for having bad luck, you need the second derivative to be positive in 2D. And naively, I'm not sure it's true, but naively 50%, right? And 50% of the cases where the first one is 0, also the second is positive. In 3D, you have two directions and you have to compute both. So already two derivatives, like 2 second derivatives, must be positive for bad luck. If one of them is negative, you have a way out of this minimum. If you go to 4D, and I found this nice graphics here, how to visualize that, I can't really, but you have 3 dimensions already, which all must be second derivative positive. So it's like, where are we now? 12.5%, like 1/8 or something, that we are getting stuck because in every other case, there's one dimension at least where we can go down. So the higher the dimensions, the less probable it is that we have bad luck. And here we don't have 4 dimensions, we have 768. So there's basically no chance that this happens. It can happen that, this is why AI scientists might become nervous when it doesn't go down. When you learn too fast, then this can oscillate between around something. So there are some other effects which are bad, and that's why you have to move slow to a certain degree. But you want to be fast because you want to be faster as than your competitor. So there's a balance you have to find when it's safe and fast, and yeah. And we don't see it here anymore. If I scroll up, you see something called learning rate. Where is it here? It's like 5-10 thousandths or something. And if you looked carefully in the beginning, we started at 0. So when you have random values, you start very slowly to learn, to train, because otherwise you get chaotic behavior. So you have to keep this value in mind and keep it at a reasonable size. All right, I promised you this is the hardest part. What does it give you? Like our steps here, it gives you basically a second. We can train on internet data, and it will not get stuck. It will always improve, right? Now let's go to the first goal here. We have to understand, why is this model doesn't make sense, right? And to do that, so let's zoom in. On the left side, again, this is a attention all you need paper for translation. We don't have that, we have the right one. And some parts of that we already know. We know, of course, inputs, right? Inputs and tokens. The cat sits, it's like this token input. We know what embeddings are, those red vectors. And if you put them all into a big table, lookup table, all of them, 32,000 of them, all 768 height, you get token embedding. It's just a lookup table, nothing else. And you can program that in C++ or in whatever Python language very easily, right? And it's interesting that you have this line here to the top. We have an LM head, it's called. It's the same metrics, the same data. Just think about takes a token embedding, put it here, and eventually, so the whole network computes now on the cat sits, but of course in vectors, right? So we have 3 vectors going through the network. And at the end, you have, again, three vectors coming out here. They go into this block here. What we do now, we take the 3 vectors, and for each of them, we look through all 32,000, do the dot product, you remember this is similarity, and find the one which is the best one, like the nearest one to your computed vector. And hopefully for the cat sits, so for sits, the third one, the vector which you get here at the end is on, right? This is what you hope for. And yeah, it's the same metrics, so the same weights. All right, we have many more blocks here. Layer norm, sounds scary. It's super simple. And it happens here, you see it after every block, basically, after or before every computation. What it does, and I don't go into the mathematics here, the cat, when it goes through the network, it computes. And it changes, like the vector, in the beginning I said there's lots of space inside. So we are putting more and more data into the cat vector, in the free space. We store data, like in a computer, we store something in that. And those numbers might get bigger and bigger or something, or they get a bias towards positive or something. Layer norm just normalizes them around 1, so standard variance and mean value. You remember that from statistics. This is what is put into formulas here, but basically it's this idea. Get more or less normal, similar looking vectors again. So we make, if this is a vector here, we make every of those the same length, right? And put them around the 0, so it's balanced. All right. With that, we understand token embedding. We understand that at the end, we compare to the whole vocabulary, which is the nearest token, and the output are tokens. We know all those light green boxes, and now we get to the most interesting bit, attention, right? Attention is all you need. Sounds, yeah, what does it mean? Is all you need. And this is a big insight, what the Google people therefore for translation had. And before I go into what it really does, I want to show an analogy. This is again the von Neumann architecture, right? A CPU. Some of you will have, who has done assembler at some point in some university, couple of hands. CPUs have registers, right? There's X, Y, A. In some other architectures, they are numbered R1, R2, and so on. But basically, there are registers, and they are the fastest memory you have, right? But you don't have much. You just have some bytes or kilobytes or something. Imagine every vector, every embedding, like the cat, right? The red vector is such a register. And there's space. You can put more stuff inside, so you can enhance that vector. And attention is the left side of a CPU. It's about an internal bus, about moving around data. We will come to a neural network later on, a very simple one, which does the computation, like can do addition, can do multiplication. We will see an example where it complements colors, for example. Okay, so let's go to the bus here, right? It's moving around data. Moving around data, so we have this sentence. This is the input, it's our context. And moving around data means to enhance words with the information from the words before. So a table, just a table, it doesn't say doesn't say anything. But imagine we encode in the table, in the free space, that the table is something, is a table, but something is on it. And next step, we extend it to table is something with something on it, and the something is sitting. And then we also extended that the cat is actually sitting on the table. So it's still the table, but it has this meta, it's extra data, which encodes that there's a cat on it. Okay. And attention, and there are many words here, causal, multi-head self-attention. Self-attention is what we saw the Google people originally. They did attention here, attention, but they did that between the German sentence and the English sentence. But OpenAI saw that we can do that on the same sentence. Like the cat sits, does attention, we will learn in a second what it is, or against itself, basically. That's about itself, self-attention. And what is causal? Causal, cause, und Begründung, something like that. imagine we are training, and we are training, so you remember this picture, right? We are training the next word of every of the words here in the context. And imagine we could move information in each direction. So when we look on sits, right, which other words which information can be put into sits? Yeah, if we can put the on here, we already know what the next word is, right? Bad. That's not what we want to train. So what we do in attention, we restrict the possible move of information in a way that only sits can send information into the table. So it's always forward. When we send a word here, it's always coming from the prefix before, never from the future. And there's a mask, an attention mask in the code, which encodes that, like it's a how do you say that? Like in the upper part of the matrix, there are always zeros, which is masking those possibilities out. And how this is encoded is in three matrices. So basically, the intuition is what we want to do. The table asks every word before, what can you offer? So it does a query, like a database query. And the word says, okay, I can offer this one. And then you say, is a query and the thing the sits can send as information, are they equal, similar? Dot product again, right? Similarity is always dot product. If it's positive, then sit sends information to the table. Like in the table, it's encoded that something is sitting on it, right? And what we send there, there's a third matrix here, V. The sit sends a V to the table. Basically, we encode something is sitting, and the something is sitting is a V into the table. It's all intuition, right? It's not really what happens. We are giving the model basically the ability to train into this direction, into this intuition. And when you look here, so I have some pictures, and you might be reminded of your electrical engineering class. This is, if it's sharp eventually, it's a 4-bit binary adder, right? And this is a fixed design, a human designs it, right? You have to imagine now we also have those gates here in our model, but the connections are completely free. The model learns that. That's the intuition. Similar here, it's a flip-flop, the most basic memory. And the question is, I mean, this attention here, like we have a memory bus, right? Sits can send information into the table. And if we go back here to the CPU analogy, it means maybe the 0 register can be copied into the N register. And there are commands in the CPU to do that. Okay, so we have one more word here we have to talk about, multi-head. Of course, there's not just one attention. There are, so I didn't say that yet. We have 12 layers in our NanoChat model. If you go to a modern model like GPT or something, GPT-5, they had 100 or something like that. But we have, so I go back here to the architecture. Here's the red one is the attention. And you see already there are multiple, I'll talk about this in a second, but attention plus something, it's a feed-forward network, I'll talk about in the next piece. And of those layers here, we have 12 after each other in our model. But in each layer, we also have multiple heads, and this is what we see here now. So imagine we can do this copying of information, but we have multiple ways, and you can imagine it's a bit like a scale loop. So you look on table, and you look on that and find your query somewhere. It's a subset or subvector, and you can also apply some rotation, projection, and some linear transformation. And every of those can mean something different. So it can be that one attention block defines something or says something about word order, another one about finding the subject to a verb, right? Every of those attention blocks can encode different algorithms, if you want, or different strategies to move data around. And so, yeah, this one we just saw, it's something about geometrical graph. You could imagine some algorithm counts or looks at the characters. Like when you want to write a poem, right? You want to how do you say in English, Reimen. So then those vowels play a role, and you could imagine such a head does this analysis and puts the right information to the table. The table rhymes with something else. I don't know. So, and on every layer we have 8. We have 12 layers. So we have, in our model, we have 96 of those devices, multi-attention heads. Yeah, and of course you can do this all with matrices here. I skip that. Everything is mathematics. Everything is here linear algebra. Can be computed. All right, so attention is sending information around between vectors. And the vectors become more and more knowledgeable about the sentence, right? At the top, the table knows exactly there's a cat sitting on it. The last bit, so we are nearly through to understand the components. There is something called a feed-forward network, and there is this term ReLU. ReLU sounds scary, right? ReLU is a max function, and some people thought in different fields, not mathematics, ReLU is a cool word. So it's called ReLU. And let me find that. So here. Neural networks, some of you might have played with them maybe years ago when they were interesting. This is the most simple neural network. It's just basically one nonlinear layer, just with maximum functions. So it's just this function we have seen before. Nothing else, very simple. And what we do, so basically, so imagine here this on vector, right? It goes through attention, it's learning, it's not only on, it's maybe on and the cat sits on it, right? It's enhanced. It goes into this table here, into this block of a neural network. And there's one phase, so it's just a matrix multiplication, which selects certain values out of the on with sitting cat, basically this vector here. Then it does maximum, and then it's scaled back into embedding. So afterwards, we might have a table, right? And an example helps to understand. So take the red color here. So the red color could be encoded maybe in 4 dimensions, right? And we blow it up, like we make it wider, a bigger vector. Here in the case, I've taken 6 dimensions. So we have multiplication, which maps that to RGB and some other values, right? Those here are not interested. Like minus blue, the blue for red is minus because it's of course not blue, right? It's a negative value. Same for green. We don't care about them, so we use the max function to hide them. And then you are saying like the other positive values fire. Fire means they are not zeroed out. And then we have another W2 matrix which takes that into another color, but now it's a cyan color, so one we want to have. The factual data of a network, like Paris is a capital of France, right? This data is mostly encoded in the W2. So it's a factual, it's like a database, the static data which is learned. And I love this tweet here. Maybe you know that, right? Is even function. Somebody asked, how can I make it better? Because I have to write down all the cases for even what's like true and false. But this it cannot compute 13, right? Because 13 is not part of it. So he asked, can I do that better? And it's an easier way. He learns, right? And the models do that, right? Models don't just learn facts like here. They are forced into that. And you can imagine the attention and the neural network can encode such a function, right? Just by intuition, you could imagine this works. And coming back here to our goal, so we are here now, our architecture could encode such an algorithm, pattern matching, right? Could do it. And by 2, we know it will do it if it's necessary. Very powerful. So we are nearly at the end of the architecture. What do we understand? We understand embedding, normalize the vectors back to like standard variation. We understand that self-attention, like the heads, the multi-heads are here. We need one bit here, this box we haven't understood. The cat sits on the table. The table sits on the cat. It's not the same thing, right? So we need some concept of position. How do words sit relative to each other? And now here I have my vector toy again. what we do is we rotate. When they are near to each other, we rotate a bit. If they are far to each other, we rotate a lot. And we do that in different frequencies. So basically, you remember rotation matrices maybe from your past. And they look like that, like cosinus, sinus, and those blocks of 2 dimensions. And each dimension has a different frequency. So the model should learn to understand distance. And it should also understand whether it's a giant distance, like 1,000 characters or tokens away, or it's like 2. If it's like next to each other, it's probably the article, right? This is something that matters. So we are applying such a metric. And again, I said the red vectors have lots of space, right? And we just use some of the space basically to encode position. And this goes into the attention. There's a trick to put that into attention. We are applying that to Q and K. We saw those matrices before. Okay, so we know that we have to recombine the attention result. There's this little blue box here. The last thing is we have this thing here called a residual. You cannot read that maybe. Everything which is computed here, like the information which is added to the vector, like table is enhanced, but you want to keep table, right? Shouldn't be banished in the computation. So that's why there is this plus, right? We take table, keep it with a plus here, and we are computing the V, like those. I mean, in attention, you had the V, which is actually sent around, right here. And this, yeah, here it is. So we had query key, and the V was sent around. So the V comes out here, comes out of the attention. I have to find the right picture again. Here the V comes out. We take a linear combination of all V's of all heads, like there are multiple. We add everything together into the vector, and now the vector has more information. We do it in the transformer case here 12 times in our model. Modern models have more. We normalize again, and then we compare with all the outputs, all the embeddings, 32,000, whole vocabulary. And then we have tokens again. Last thing is missing. I always hear that LLMs are probabilistic. They are not deterministic. It's false. LLMs are deterministic. Everything here is just matrix multiplication, and if you fix the weights, like eventually you will fix weights here, right? We can maybe take the time, take a look where we are. This is getting better here, right? Auftrag in Deutschland is still not good, right? But it understands it's something about locality inside of a country and whatever, Gemarkung, Einwohnerzahl. It's something, still garbage, but it's getting better. All right, so this is the architecture, and you can imagine this system here can encode some amount of computation, right? Not everything is limited, but it can encode a bit. And as I said, the embeddings are learned. And let's take another look on embeddings. So this we have seen already, right? Embeddings eventually come out, and I took my model, like not the fresh one, but the one which I had trained before. And I took some examples and I compared them. You've seen that before. And you can even go one step further. I can do mathematics. This is, I think it's crazy. So we take vater, so the embedding vector vater. I do vector subtraction minus Mann plus Frau. And it knows that it's mother. And they can see that there's so much of world knowledge in an embedding already. And this is not even about attention and stuff, right? This is just the embedding vectors, very simple. This is maybe the most amazing here, Dresden, Sachsen, Hessen, right? Dresden minus Sachsen plus Hessen is Wiesbaden. So, and you can basically understand, in Dresden, there is knowledge about, I mean, also 3 words, there's knowledge about Wiesbaden, right? It's somehow encoded. If you have 3 of them, you get the knowledge. And even like plural here, plural Hunde minus Hund plus Katze gives you the plural of Katzen. It's amazing, I think. And there I mean, this is obvious, right? It has knowledge, world knowledge, and can do pattern matching, everything. It's not just learning, it's more. It's building structure. All right, we are training. Maybe the last, maybe few things. We are nearly at the end. So Hugging Face, I showed that before. This is our data. So you can get many data sets and use them for training. If you work on that, like there's a GPT-2 model, right? It's one file which has 300 lines or something, and I have it here. So in my slides, I have it printed out, and I try to find everything of the other slides. Where is it actually used, right? So I don't know what is a good example here. I don't know. Take a random one. You will see here are the embeddings. I had to turn it around because source code was from top to bottom. So now it's turned around. So the embeddings happen here. It's one line, and then you have the blocks, but n times, right? There's a range. There's a loop because we have 12 of them. Layer norm is the ln. This last comparison with the vocabulary, it's again, it's LM, it's a linear transformation, and so on and so on. So everything can be found here. There's not much more actually than that. Maybe, one last thing which matters. So what we get, so we have inputs, which are those red vectors. They go to these transformer blocks, attention plus neural network. Then we normalize, then we compare it with all vocabulary embeddings. And then we get out numbers. Like the result of comparing that are vectors, and the vectors look like that. So imagine the cat sits on the, right? What is the most common word? The one with the highest linear, the highest dot product, the highest scalar output. 29, table has 29, cool. So I have table. But there are more words, right? And maybe I want to convert that to probability. So we can convert that, and softmax function is such a thing to convert. So we get a nice vector, and we see 80% is table, 90% is whatever, floor or so, right? I said those models are, they are deterministic. So I started here, same model, just I call it the chat function. And der Sinn des Lebens ist, and you would expect now it computes to completion, and it gets something which, I don't know, might make sense once in a while. It's really, really good. Sometimes it's just garbage. But the thing is, a chat always has a different answer, right? You know that from GPT. But this is artificial. And the trick is, we don't take always the 80%. We take like the top 10 of the words and then randomly choose one. And why do we do that? Because we want some diversity in the answers, right? Otherwise it's boring. But it's an artificial feature of chat. Okay, and what else? Just some keywords. Mixture of experts. Who has heard that? You have, I guess. Sounds also like rocket science. It's not. Here is the neural network we have seen, like the one which is this red to cyan complementary color thing. And I said that in those matrices, there's most factual data. If I want to encode a lot of data, like I want to encode the whole Wikipedia. If I want to run a model on my computer, maybe my computer is too small for the whole Wikipedia, at least in a GPU. What you can do, you can basically split it up, make one neutral network here. Maybe it's for IT knowledge, right? Another one is for language knowledge. Another one is for whatever, right? And those are experts, but they are nothing else than the neural networks, like this box here. Is it this one? Just multiple of them, and we put a router in front, like another small matrix which chooses like 8 of them, and then we compute 8 of them, combine it again. And here you can already see you could shard this model on many nodes, right? Maybe one node has the left half, the other one has the right half. Or maybe we swap it in from disk or something, and I guess we might hear more about that. That's a mixture of experts, so it's not rocket science. What else? What is interesting? Where are the weights? So here I calculated where are weights. Weights are mostly in the textual data in this neural network, right? 45%. The embedding vectors, like this big lookup table, 32,000 columns of 768 long vectors, it's 30%. Attention is 20%, a bit more. And there's some stuff like in the layer norm, there are also some parameters like bias and a scale. But yeah, you see, that's it. And the last thing, KV caching. Will you talk about KV caching? So just a hint, because this matters when you want to run AI in your data center. We did training here. training means, and you saw attention before, we do this method here for every word against every other word, right? If you have a context of 100,000 tokens, which is normal today, 100,000 times 100,000 is how much? Can anybody calculate? It's a big number, right? If you put all those similarity computations into the matrix, you get this attention matrix. And this is growing quadratically with the context links. That's why big contexts are expensive when you want to use them. And there's one insight, and this is a KV caching. When we learned in the beginning that you feed in autoregressively the input again into the same prefix that you append and you compute. If you do that, and you look at the metrics, everything here in the middle, like the previous words and how they compare, right? How they send information doesn't change. It's the same. It's unchanged. So when Vasu goes to GPT and types something, the GPU can cache his vectors, his matrices. And we only have to compute the next word, like the new word, which was just appended to the input. So it's becoming a linear problem in inference. Training and inference are very different, that's why. And if you look on the matrices we saw before, for attention, there was this query, there was a key, and there was a V, right? SIT sends information, V to table. That was our intuition. And if you look on the matrices, this is SITs, this is SITs, and this is table. If you add a table to the input, everything about SITs stays the same. That's why this part of the equation we can cache. We don't have to recompute every time. And that's why it's called KV caching. And we need lots of memory for inference to do that, but it makes inference cheap. All right, that's, I think, all I had. Just some pictures here. I tried llm-d a couple of times and it gets something. It's a super small model, obviously, so it's not GPT. But yeah, that's all I wanted to show. And I hope I have convinced you that you can believe the same thing as you did for computers, that LLMs can encode world knowledge and work with it. Thank you. Yeah, if that's fine.
I have a question. So on the attention hats, you said in your example you had like 12, and they're filled with different aspects.
Mm-hmm.
How is it decided like which aspects are important?
Learning.
So it's part of the training data?
Basically, the only thing you do, you give it a framework to implement attention. All the weights, like the decisions you are asking for, they are unset, like they are random in the beginning. And you are trusting the mechanism of optimization. This is the thing here we showed in the beginning, right? That we can decrease loss. So if there's a way to compute certain pattern matching algorithms, this model, if it's big enough, obviously, will learn it. That's a trust you have to have. No, training. This is training. So the only thing, oh yeah, I didn't show one slide, and I want to show that because I loved how I asked OpenClaw using Opus about this intuition, which I just showed you, and it came up with this here. Darum sind GPUs so geil dafür, and I love that. If you look on the networks, this gives an interesting different aspects. So we are sending in tokens. We are getting the embeddings, right? 3 embeddings here in this case. All components here, I try to draw that, they are just operating on one token. The only component which does interconnection bus, right, this word we had, the only thing which does that is the attention. And obviously everything here is parallelizable, or you can run it on a parallel machine like a GPU, right? Everything is matrix multiplication. And even self-attention is just 3 matrix multiplications if you want. So that's why it's optimal for GPUs, and backpropagation works because differential functions. And as I said in the beginning, the matrices are just a simulation of an analog computer. Everything about intuition I told you is about vector spaces and real numbers, not about matrices. Matrices just compute a simulation of that. So there's one bit about inference. the space is limited, right? The vectors, I mean, they have a lot of space, but still is limited. And you have 12 layers. So a network can only compute a certain amount of pattern matching and word knowledge and so on in one pass. But what people found out, so after GPT-4, then there was this 4.0, maybe people remember that I think Raspberry, or how they called it internally, basically it was the insight when we want to compute more, like do more interesting inference, we have to make the model think, because thinking means we have a longer context always going through the model. So the model has an ability to, I mean, we have some vectors which have space, right? In a computer, we also have a cache, we have main memory and so on. Imagine the sentence, the context becomes another layer, a higher level of memory. It's much slower, like it's in milliseconds or hundreds of milliseconds access rate, but you can store even more knowledge when you just keep thinking. It's like when you read a book, right? You are improving your intuition about the book. You're summarizing things from the beginning, and you build abstractions in your head. And the same thing happens when you compute. So thinking is a way to externalize that into inference, if you want. Yeah.
So you compare ChatGPT or Claude or whatever, do they mainly differ in their architecture or in their
No. I mean, there are lots of tricks, right? There's an Opus model which can have 1 million token links. You can use that. It's expensive, we can use it. They will not compute 1 million times 1 million attention. They will not, because you can compute, I mean, you can make up the number, right? It's giant. Nobody has so much memory. So you have to optimize how you compute attention. And there are lots of tricks inside. Like there are, you might know the terms fast attention. Huh? Yeah, there are several. I mean, this algorithm is like the perfect one, but you can optimize everywhere. And this is happening in the labs, right? Plus the size, 100 or more layers. Bigger vectors, our are 768. I'm not sure what GP2 uses, maybe 10,000 or so. And they use like, is it terabytes of, no, tera tokens? What is the number nowadays? I don't know. Much more than our 3 billion. So everything gets bigger. Yeah, and of course, I don't want to hide where things are coming from. So I'm not the first one explaining those things, right? Karpathy has great videos. Watch them. You have a good start now to understand them just by watching. I've shown a lot of the things you will explain in more detail. And this is amazing here, like 10 days ago or something, he tweeted all the mathematics we have seen, he encoded in this Python program. So all the mathematics to train is in 343 lines of Python. It's not GPU optimized. Don't run it. It's slow. But there's not much more in it. 250 lines drive our new world of AI, basically. What?
Want to share those slides?
Yeah. Yes. Yeah. Yeah, and what was the name? Like they learn the embeddings for, but yeah, but what I read is that it doesn't scale. Like when you go to scale just a bit about GPT-2, it doesn't work. It's getting bad. And nowadays they use those positional embeddings via the rotations. It's better. And there are papers about that, so you can read up about it. What else? I mean, I didn't look at that. He does lots of optimizations nowadays. Like he brought down the training time by a factor of 10 or something by more optimizations. I did some of them. He also did like, so imagine your chat, like your 100,000 codecs or Claude Code tokens, right? 100,000 tokens go through the network. Everything here is, I mean, the whole context goes through that, right? 100,000 times, I don't know, 10,000 dimensions, you get into the gigabytes of data per user, right? It's lots of data. So everything is about using, moving data around in one GPU, across nodes, right? If you do the slide, I have the slide here. If you do the mixture of experts and you have multiple nodes, right? You have to move the data through the network. So you think about how to get smaller data. I start with 32 bits float numbers, right? This is standard FP32. You can just use FP 16 bits, and there are some variants in NVIDIA to do that. And you halve the size of every embedding, and you halve the size of the memory moved around. There are many optimizations. There are many ways to improve here on the, I don't go into details, but on the CUDA level. The CUDA is a library for GPUs from NVIDIA. And you can compute and you can apply algorithms, and there are things like compiling those networks into one blob of basically like a compiler when you bind, right? When you bind everything together in a binary, send it to the GPU. And one famous example, there's something called flash attention. So you can basically replace the full attention block we had there. Don't do it manually like I did in the beginning, but just use the library, and they highly optimize that manually in whatever level, not C, probably it's even lower than that. And then suddenly you have a factor of 10 of speed up. So there are many ways to optimize that. Yeah.
Studied languages, specifically English, for quite some time. And one of the main differences between languages is between compounding languages, like German, for example, you explicitly made the example of the Dampfschifffahrtskapitän, for example, which you can't do in English. You can't just like put words together, obviously. So for me, the interesting thing that I was thinking about the whole time is about the optimization that you have to do for compounding languages.
I mean, the model learns, right?
Yeah, but I think that there's maybe that they have to do some tricks there. Because as we've seen in your slide, so it learns the space between the words in English.
Yeah. Right? I mean, it learns, if you train with both, it learns it for both, right? Yeah. What I noticed here in German, if you have those words, right, there's Wurst with a capital W, which is a single word alone, and then you have a small W Wurst, which is like in those sentences. Yeah. So we are already wasting tokens in the tokenizer, half of them roughly, or something like that.
Step or optimization in the embedding phase actually makes sense, and this absolutely, funny enough, it absolutely matches what I experienced when I used ChatGPT or Claude or whatever with German, that I usually get worse results with that. Yeah, and this makes total sense now. So thanks for that.
There's a whole video from Karpathy about tokenizers, and I don't know, the cat sits on. This is now the GPT-2 one. And they are open again. You can look into them, how they work, and they have like crazy hacks, which like when you have source code, it's even worse, right? Source code has those special constructs. JSON is worse than other languages, and so on. So there are crazy amount of optimizations on this layer. I haven't done it, but tokenizers matter, for example, just because of those reasons.
Size of the embeddings? Is it the
those are called hyperparameters, and when you build that, you just choose. It's just it's a variable in your source code, and because GPT-2, GPT-2 did that. Yeah, in one embedding, one token basically, and you can take 1024 and just compare. Right, you train twice, compare it's better or not.
Stefan, very much. You sit here, we'll have some pizza, and then it's 1 minute, half an hour, and then it's on. Okay?